Let's get started. So I introduced the concept of convex sets and convex functions in the previous class. A convex set is one where uh, given every pair of points within the set, the line segment joining those 2 points also lies within the same set, right? So for example, this is convex, where this shape is not convex. Now, what we're interested in are convex functions, and convex functions are generally defined over convex sets. So we say that a function is convex if the line segment joining any 2 points on the curve always lies above the curve. It never goes below the curve. All right, and we say that it is strictly convex if this inequality is a strict inequality except at the endpoints. So f of alpha x plus 1 minus alpha y is strictly less than alpha f of x plus 1 minus alpha f of y for all alpha in 0, 1. Okay, and correspondingly, we say that a function is concave if minus f is convex. So if a convex function is one which looks like a bowl, whereas a concave function is one which looks like an inverted bowl, right? So you flip it, and you get a concave function. Okay, so this is the formal definition of a convex function, but you may have seen this in a slightly different way in your maybe plus two or the first year of your undergrad. Right? You say that a function is convex, or this is a necessary and sufficient condition for convexity. So a function is convex if and only if the second derivative is greater than or equal to 0. Right? So assuming, of course, that both the first and the second derivatives exist. So if both derivatives exist, then it is convex if and only if the second derivative is greater than or equal to 0. Okay. I'm not going to prove this statement, but you can find the details in the lecture notes that I've posted on the web page. So the function is strictly convex if the second derivative is strictly greater than 0 for all x in a comma b. Okay, but remember that this is a necessary and sufficient condition, assuming that the second derivative exists. So, for example, there could be a function for which the second derivative does not exist at all points, but it could still be convex. Okay, and similarly, if what is the corresponding condition for f to be concave? What can you say about second derivative?
Second derivative less than or equal to?
Exactly. So the second derivative of x should be less than or equal to x for all x in the corresponding interval. Okay. So let's yes. Any question?
0, no, sir. Second derivative less than or equal to?
Oops, sorry. Less than or equal to 0 for all x in the corresponding interval a comma b. All right. So let's look at some examples. Let us first look at log x. Okay, before we even sort of try to compute this, try to see the second derivative or whatever, let us think about it. So what does log x look like? So if you just sort of draw a picture, log x looks as the following form. It looks somewhat like this, right? So is it convex or concave? Concave. It's concave, right? So we should expect this to be concave, but let us see if that's indeed the case. Let's take log x to base 2. So this is my f of x. Now can you compute the second derivative? So f dash of x is Let me write it as this is d by dx of log x to base 2. I'll write this as ln x by ln 2. So this is 1 over x ln 2. So what is the second derivative?
Minus 1 by x square ln 2.
Correct. It's 1 minus 1 by x square ln 2. Of course, we're defining all of this for x in the interval 0 to infinity. So it's only for the set of positive reals. And what can you say about f double prime of x? For x in 0 to infinity?
Less than 0.
So it is strictly less than 0, right? So this is a strictly concave function. Okay, so now what about x square? Is this convex or concave?
Convex.
Convex.
It's convex, right? So if the curve is going to look something like this, it's like a proper bowl. What is f double dash of x?
2.
It is 2, which is strictly greater than 0. So it's again strictly convex. Okay, let's do one last example, x log x. So what is f dash of x going to be equal to?
One plus log x.
It is 1. Are you sure it's just 1 plus log x?
So
Assume that the base is 2.
land 2 will be there. 1 by land.
Yes. Correct. So let's write it in this particular form. 1 plus ln x by ln 2. Okay. So what about f double dash of x? The second derivative?
One by x into land 2.
Correct. And what can you say about this? Again, x is in 0 to infinity. This is always going to be, well, it's again strictly greater than 0, right? So this is another example of a convex function. Okay, so just keep this in mind that x log x is convex. We'll use this in a few minutes. Okay, so fine. Why are we so interested in convex functions? We're interested in convex functions because such functions satisfy the following interesting inequality. So if you have any convex function f, which is defined over, let's say, the set of all reals, and x is any random variable. Okay, x is a random variable. Obviously, it takes real values. Then the following holds that the expectation of f of x is always greater than or equal to f of expectation of x. Okay. So if I take f of x, so I look at the random variable y equal to f of x. So this basically says that the expectation of y is greater than or equal to f of expectation of x. Okay. So let us look at this interesting inequality. And first, let's look at some examples. So take f of x equal to x squared. Okay. So what does this say? It says that. So first is x. We just saw that x square is convex, right? So we know that this is convex. So therefore, we can apply Jensen's inequality. So this says that expectation of x square, which is expectation f of x, is always going to be greater than or equal to f of expectation of x. So f of x is x square, which is expectation of x, the whole squared. Okay, and you've seen this before, right? So this implies that expectation of x square minus expectation of x, the whole square, is
Variance.
greater than or equal to 0. Exactly. So this quantity, the expectation of x square minus the expectation of x, the whole square, this is just the variance of x. And you know that the variance is always non-negative. Okay, so that's an interesting property. Now let's look at another example, log x. So is log x convex?
No, sir.
It's not, but what we do know that it is concave, right? So minus log x is convex, right? So let's try to apply Jensen's inequality of this. It says that expectation of x of f of x, which is the negative expectation of log x, is always going to be greater than or equal to minus log expectation of x, right? So this implies that the reverse is true. So the expectation of log x is always going to be less than or equal to log expectation of x. All right. So in general, suppose that f is concave. Right, f is concave, then what can you say about expectation of f of x versus f of
It will be smaller than
expectation of x? Exactly. So in Jensen's inequality, if f is convex, then expectation f of x is greater than or equal to f of expectation of x. Since if f is concave, then minus f is convex. So expectation f of x will always be less than or equal to f of expectation of x. Okay, so this is very useful, and we will, in fact, right away we'll apply it on a particular function. So we just saw that the function f of x equal to x log x is convex.
Sir,
Okay.
1 minute.
Yes.
So we are taking like the expectation of f of x and f of expectation of x in both
Correct.
convex and concave case. So in convex case, we are able to comment about variance. If we use that here, then
But x square is a convex function, right?
okay.
Right. So we're talking about general functions here. For a specific, so this is a specific example where f of x equal to x square. Since x square is convex, we can say that expectation of x square is greater than or equal to expectation of x the whole square.
Okay, sir. So I'm just asking. I don't know if it's correct to ask like this, but if we take minus of x, it should be concave. So
Okay, so you take minus x square, which is concave. So let's take f of x square f of x equal to minus x square. We know that this is concave. So expectation f of x is minus expectation of x square is less than or equal to minus expectation x the whole square. But then if you just rearrange, you're going to again get expectation x square. I take this on the right hand side, expectation x square minus expectation x the whole square. This is greater than or equal to 0. So it's still the same thing.
Okay, sir. Thank you.
Right? So there's no contradiction over here. Okay. Now we have f of x equal to x log x, which is convex. Okay, and we want to use this to prove the following inequality. Okay, it's called the log sum inequality, and it says the following. So suppose that I have a bunch of non-negative real numbers, alpha 1, alpha 2 up to alpha m, and beta 1 up to beta m. Okay, maybe these are 1, 3, 0 0.5, 0 0.6, and 2, 5, 7, 100.1. Doesn't matter. So I take two pairs of, or I take a pair of of these strings, numbers or sequences, both of length m, alpha 1 through alpha m and beta 1 through beta m. And I wanted to also satisfy this sort of technical condition that if beta I equal to 0, then alpha I equal to 0. So for example, if alpha I is 1, 3, 0 0.6, 0, 0.7, if this is my alpha sequence, then my beta sequence must necessarily so this can happen if my beta sequence is 0 0.2, 1, 5, 0, 0 0.7, that is okay, but the following is not okay. So I can't have a 0 0.7 here and a 0 here. So if beta I equal to 0 for some I, then alpha I must also be equal to 0. That's just a technical condition. For now, for simplicity, let us assume that both alpha and beta sequences are strictly positive. Okay, so I have m positive real numbers, alpha 1 through alpha m, and m, again another set of m positive real numbers, beta 1 through beta m. And I compute this summation I equal to 1 through m, alpha I log alpha I by beta I. Okay, the claim is that this quantity is always greater than or equal to the summation over all I alpha I log summation over I alpha I by summation over I beta I. Okay, so maybe let's just take the following example. So I take alpha I to be 1, 3, 0 0.6, 0 0.7. Okay, so let's just take 4 numbers. So this is my alpha, this is my beta, which is, let's say, 2, 0.3, 0.1, 0.8. Okay, say this is my alpha and this is my beta. Can maybe one of you compute the left hand side, summation over I, alpha I log alpha I by beta I? What is that going to be?
577.
How much?
RHS. You said?
What is the LHS?
I calculate RHS.
Okay, so what is the RHS?
3.85.
Correct. So it's 3.85 something.
77.
This is the sure 3 point something. What about the LHS?
10.38.
Correct. So it's 10.38 something. So clearly the left hand side is strictly greater than the right hand side. Okay. So that's interesting, and in fact this holds for any set of real numbers. Okay, you can, no matter how you choose these real numbers, as long as this particular condition is satisfied. In particular, if all the alpha i's and beta i's are strictly greater than 0, then this is always satisfied. And this inequality is an equality if and only if all the alpha i's are equal to all the beta i's. Okay, so equality only if alpha I equal to beta I for all I. Now let's sort of look at this particular expression over here. Have you seen a similar expression before?
Like probability we had in this
Correct. What does it look like?
KL.
Exactly. So it looks like the KL divergence, right? Except that the alpha i's were the sort of P of x and beta i's were the Q of x. Right? And in fact, that is what we want to use this for. This is a more general inequality, but in fact, we'll specialize it to probability distributions. But before we go to that, let us try to prove this statement. So we'll assume that we have Jensen's inequality. Okay, suppose we have this particular inequality over here, and we'll try to use this to prove the log sum inequality. Okay, now, so we know that if f is convex, then expectation f of x is greater than or equal to f of expectation of x, right? Or if I sort of expand this out a little, then this is the left hand side is summation over all x, p of x.
Sir, if
Yes.
alpha of all alpha is are equal to beta I,
Okay.
it becomes 0 on
If all the alpha i's are equal to beta i's.
log we have, so
Correct.
it will become 0 on both sides. So that is the only
Correct.
Okay.
Yes. So okay. So this is not the only case. In fact, it's a good point. It's equality if alpha I equal to beta I, but in general, if alpha I equal to some k times beta I for a fixed constant k.
Okay.
So this is another condition. If alpha I equal to k times beta I, then note that this is always going to be log whatever 1 over k, right? The LHS will be summation over I alpha I log 1 over k. And the right hand side is also going to be summation over alpha I log 1 over k. Okay, so let's look at Jensen's inequality. What does it say? So it says that summation, the expectation f of x is greater than or equal to f of summation over all x P of x times x. Okay, and our goal is to somehow use this. Now let's start with the left hand side, which is summation I equal to 1 to m alpha I log alpha I by beta I. Okay, so all we have is that the alpha i's and beta i's, they're all positive. Let's assume that all the alpha i's and all the beta i's are strictly positive. But that doesn't mean that the alpha i's form a probability mass function, right? I somehow want to bring the left hand side to this particular form for some f. Okay, so let me do the following. I take summation I going from 1 to m of beta I. I'll multiply and divide by beta I log alpha I by beta I. Okay, I've done nothing but multiply and divide by beta I. All the beta i's I'm assuming are strictly positive, so I can do this. Fine. So this has this particular form, right? So this looks like x log x. Correct. So that is good. I have x log x, which I know is a convex function, but then it's not exactly an expectation of x log x. If the beta i's formed a probability mass function, then this would be in the form expectation of x log x. So let's try to bring it to that particular form. So I equal to 1 to m beta I will now multiply and divide by this quantity b, which is summation over all I beta I. Okay, so this alpha I by beta I log alpha I by beta I, where this term capital B is summation I equal to 1 through m of beta I. Okay, so let us look at Pi equal to beta I by capital B, which is beta I by summation I equal to 1 to m of beta I equal to 1 to up to m. So this is a valid PMF, right? So each Pi is greater than or equal to 0, and summation I equal to 1 to m of Pi. So that is summation over I beta I divided by, let me use a different index for the denominator just to avoid confusion. So this is beta I by summation over j beta j. So this is I equal to 1 to m beta I by summation j equal to 1 to m beta j, which is b by b, which is equal to 1. Okay, so now the PI's are valid, is a valid probability. So now my summation I equal to 1 through m alpha I log alpha I by beta I, this is capital B times I equal to 1 to m Pi times alpha I by beta I log alpha I by beta I. Alpha I by beta I log alpha I by beta I. Okay, so now if I say that xi is equal to alpha I by beta I, 1, 2, up to m, then this is basically in the form b times summation over I pi xi log xi. So this is precisely the form that we want. This is expectation of f of x, where capital X, the random variable x, takes on these values. So it's alpha 1 by beta 1 with probability p1, alpha 2 by beta 2 with probability p2, alpha 3 by beta 3 with probability p3, and so on. So this is good, which means, so now since it is in this particular form and x log x is convex, I can use Jensen's inequality. So I can use Jensen's inequality to say that this is greater than or equal to f of expectation of x. This is b times expectation f of x. So since I have this b over here, but what is this equal to? It is b f of expectation of x is f of, so my function f is x log x. So this is summation over I equal to 1 to m pi xi log summation I equal to 1 to m pi xi. Correct? So I had summation over I pi xi log xi. Using Jensen's inequality, this is greater than or equal to summation over I pi xi log summation over I pi xi. But what is xi? Xi is alpha I by beta I equal to 1 to m. Xi is alpha I by beta I. But what is pi? Pi is beta I by capital B. Let me substitute that in here as well. I equal to 1 to m beta I by B times alpha I by beta I. All right. So all I've done is I had alpha I log alpha I by beta I. I just multiplied and divided it by a couple of quantities to make sure that it looks like expectation of x log x. And then I use Jensen's inequality to say that this is greater than or equal to f of expectation of x, which is expectation x log expectation x. And then I've again substituted for this pi and xi. So now I can cancel this beta I and this beta I, this beta I and this beta I. All right. But then what is this equal to? This is b times summation over I equal to 1 to m of alpha I by b log summation I equal to 1 to m alpha I by capital B. Now once again I can cancel these two b's. So what I get is summation I equal to 1 to m alpha I log summation I equal to 1 to m alpha I by summation whatever j equal to 1 to m of beta j. Okay, so this is exactly what we wanted. Okay, so maybe let us quickly go through this once again. What did we want to prove? We wanted to prove that summation over I alpha I log alpha I by beta I is greater than or equal to summation over I alpha I log summation over I alpha I by summation over I beta I. Okay, and the trick we used was to use Jensen's inequality on x log x. So I first bring this to the form expectation of x log x. Right, so I start out with the quantity we had on the left hand side, and then I first multiply and divide by beta I, so that I first have x log x. Okay, and then I again multiply and divide by capital B to make sure that I have a probability mass function sitting over here. So beta I by capital B is a valid probability times capital B. So now this particular quantity is in the form expectation of x log x. And I use Jensen's inequality to say that this is greater than or equal to expectation x log expectation of x. Right, so which is precisely this particular quantity. This is expectation x log expectation x. All right, and then it's just simplification. I cancel out the beta i's, I cancel out the capital B's, and that gives me summation over I alpha I log summation over I alpha I by summation over I beta I. Okay, any questions? So the log sum inequality is an extremely powerful tool, and lets us make a lot of statements about all the information theoretic quantities that we have. Okay, so let us start with the KL divergence. Right, so I have dpq for any two probability mass functions p and q. dpq is equal to summation over all x p of x log p of x over q of x. Okay, so if I apply the log sum inequality, then what do I get? This is summation over x p of x log summation over x p of x by summation x q of x. But what is this equal to?
Sir, some.
So 0.
Yes, it's equal to 0. Yeah, Abhirami, you had some question.
Yes, sir. I was about to ask it. Summation over all x will give probability 1.
Yeah. So this is a PMF, right?
Yeah.
So P and Q are both PMFs. So summation over x of P of x, we know that this is equal to 1. This is also equal to 1. So I get 1 log 1 divided by 1. log 1 by 1, which is 0. So the log sum inequality implies that for any two PMFs P and Q, the KL divergence is always non-negative. Okay, so that's natural. That is, since I said that the KL divergence, so for the KL divergence, as we saw, is a measure of distance between distributions. So obviously we should expect it to be non-negative, right? So that is good. So the KL divergence is non-negative as expected, and there's one other point which I didn't prove when we looked at the log sum inequality. I mentioned that we have equality in the log sum inequality if alpha I equal to k times beta I for all I. Okay, so in this case, so when is dpq going to be equal to 0? So we have equality in the log sum inequality if and only if alpha I equal to some k times beta I for all I. There is some constant k such that alpha I equal to k times beta I. All right. So therefore, dpq equal to 0 if and only if what happens?
B and Q are same. We have same distribution.
Exactly. And why can it not be some constant times the other? Some non-unit constant?
So log of a positive number.
Doesn't matter, right? So let's say that p of x, okay, log of a positive number, but is it possible to even have p of x? So firstly, we saw that expectation of so to apply the log sum inequality, the right hand side is always equal to 0, correct? For every p and q, the right hand side if I apply log sum inequality for dpq, then I always get the right hand side to be equal to 0. And when does equality happen? When p of x equal to some constant times q of x, k times q of x. Is it possible that k is not equal to 1?
No, sir, because the
Why?
summation of a p of x overall x is 1, right?
Exactly. So if you take the summation over all x, p of x, this should be equal to k times summation over x, q of x. But you know that this is equal to 1. So 1 should be equal to k times 1. So this means that k must necessarily be equal to 1 if p and q are probability mass functions. So dpq equal to 0 if and only if p of x is equal to q of x for all x. Right? And this corresponds to our notion of distance, right? So dpq, as we've seen, is always non-negative, and it is equal to 0 only if the two arguments are the same. And that is what is natural, what is naturally expected in any measure of distance between distributions. But this is not a true distance. So we've seen that dpq is greater than or equal to 0 for all pq, equal to 0 only if p equal to q, but it is not like the Euclidean distance. Can you say what property the Euclidean distance would satisfy, but the KL divergence does not satisfy?
Sir, symmetric property.
Exactly. So dpq is not symmetric. dpq is in general not equal to dqp. There could be some specific distributions for which dpq equal to dqp, but in general, this is not true. So, whereas if you look at the Euclidean distance between 2 points, then this is symmetric. The distance between point A and point B is the same as the distance from point B to point A. So this is not symmetric. So that is why this is not called the KL distance, it is called the KL divergence. It is not a true distance. Okay. Any questions? Okay, so let's see what this implies. Now, so we started out with Jensen's inequality. Now, Jensen's inequality implies the log sum inequality. The log sum inequality in turn implies that the KL divergence is always non-negative. And now let's see what this implies for other information theoretic measures. So I claim that this implies that the mutual information between any pair of random variables is always non-negative. Why is that true? Can you write the mutual information as a KL divergence?
So it'll be like a joint distribution?
Correct. So it's the KL divergence between the joint distribution and the product of the marginals. Right? So since mutual information is a KL divergence, this is always greater than or equal to 0, which implies that the mutual information is also greater than or equal to 0. And when is mutual information going to be equal to 0?
When they're independent.
Exactly. So ixy equal to 0 if and only if pxy of x comma y, the two arguments are the same, which is px of x times py of y. In other words, they're independent. And that is exactly why the mutual information kind of measures how far the two how far the joint distribution is from being independent. Right? So ixy equal to 0 if x and y are independent, and it is greater than or equal to 0. It is strictly greater than 0 if they're not independent. All right. So, but as we know, the mutual information can be written in terms of entropies and conditional entropies. Right. So ixy is h of x minus h of x given y, which we know that the mutual information is always greater than or equal to 0. So this implies that h of x is always greater than or equal to h of x given y for any xy, or h of x given y is always less than or equal to x. So in other words, if you condition on another random variable, then the entropy can only decrease, it cannot increase. So conditioning cannot increase entropy. Okay, so this is a very useful property, and if you look at, say, n jointly distributed random variables x1 through xn, or a sequence of random variables, then the entropy of this sequence is always going to be less than or equal to the sum of the entropies of the individual random variables. And why is that? Just by the chain rule, you can write h of x1 through xn as summation I going from 1 through n, h of xi given x1 through xi minus 1. But since conditioning cannot increase entropy, this quantity is less than or equal to each h of xi given x1 through xi minus 1 is less than or equal to h of xi. All right, so conditioning cannot increase entropy, it can only decrease entropy, and the entropy of a sequence of random variables is less than or equal to the sum of the entropies of the individual random variables. Okay. Any questions?
So can you repeat the last point? The LHS side, what did you say? The entropy of?
So this is the entropy of the joint entropy of the sequence, right? So the joint entropy of a sequence, so h of x1, x2 up to xn, right? So this is the total information content. This is always less than or equal to h of x1 plus h of x2 up to h of xn. Okay. So, for example, suppose that let's try to look at this in the context of compression. Okay. So we've seen that if we have an IID sequence, for IID sequence xn, the best rate of compression, the optimal rate of compression is h of x. But in general, for a general joint distribution Pxn, the optimal rate is equal to h of x1 through xn divided by n, limit as n tends to infinity, right? Whatever, for a specific n, the optimal k over n is roughly equal to h of x1 through xn divided by n. All right. Now, if I try to compress this as an IID sequence, if I compressed each symbol independently, then I can compress x1 to h of x1 bits, x2 to h of x2 bits, and so on. Right? So you compress symbol wise. So you first compress x1, then you compress x2, compress x1 to c1, compress x2 to c2, and so on, xn to cn, and then you concatenate everything together. All right? Then the expected length, the overall expected length would be roughly the length of c1 plus the length of c2 and so on, which is h of x1 plus h of x2 and so on up to h of xn. Okay, but on the other hand, if I compressed it as a block, right, I make sure I design an optimal compressor by taking into account the interdependency between the symbols, the correlation between the symbols, compress the entire block, then the expected length would be roughly h of x1 up to xn, the joint entropy of x1 through xn. And basically what this statement says, h of x1 through xn is less than or equal to summation over IH of xi says that the expected length for blockwise compression is always going to be less than or equal to the expected length of symbol-wise compression. And the two will be equal only if the xi's are all independent. Right? If the xi's are not independent, then this will be a strict inequality. So obviously it makes more sense to compress it blockwise. And otherwise, if the xi's are correlated, then there is a penalty if you compress the sequence symbol by symbol. All right. Any questions? Okay, so we'll stop at this point. So there were certain topics that I could not cover in the course, mainly to do with the convexity of, we've shown that all the information measures that we've seen, entropy, mutual information, conditional mutual information are all non-negative. We've seen that conditioning can only reduce entropy. We've seen that the KL divergence is always non-negative, but there are some more properties. So the entropy is a concave function of Px. The KL divergence is convex function of the pair P comma Q, and the mutual information has the following interesting property, that this is concave in Px for a given Py given x. So if you fix Py given x and vary the input distribution Px, then the mutual information is concave, whereas if you keep Px fixed and vary Py given x, then this is a convex function of Py given x. Okay, so this means that the entropy is concave, so it achieves the maximum at only one particular point. The KL divergence is convex, so it's shaped like a bowl in the joint distribution, and the minimum point is when P equal to Q, because KL divergence is 0 if and only if P equal to Q. Similarly, if you fix a particular Py given x, then it's possible to maximize the mutual information, and that is given by the capacity, remember. So therefore, if you want to compute the capacity, which is the maximum over all possible Px of I of xy, this optimization problem is a convex optimization problem, because the argument is a concave function. So you can use any convex solver to solve this particular optimization problem. This is convex optimization problem. All right. So similarly, if you want to sort of find the worst channel for a given particular input, then that can also be solved as a convex optimization problem. It turns out to occur naturally in the problem of lossy compression, and therefore you can minimize Ixy with respect to Py given x for a given Px. All right. So we'll stop here. That sort of concludes this particular course. So if you take the source coding and the channel coding courses, then you'll see some more properties. In fact, those courses, so in this course, we only sort of looked at properties of information measures and the statements of the source and channel coding theorems. So in source coding and channel coding courses, we'll see some algorithms which are optimal or close to optimal for the source coding and the channel coding problems respectively. Okay. Any questions or comments?
Sir, this IXY is concave in P. Sorry, yeah, it is concave in PX for given PY given X.
Correct.
So we can see that from the formula, right? IXY is equal to H of X minus H of Y given X.
Why do you say that you can see directly from the formula?
Right. So because H of P of X is concave in PX, right? So
correct. So H of X is concave, but what about H of Y
if
given
X?
X?
Yeah.
So remember that H of Y given X. Okay, so it's a good point. I agree. I agree that this is a consequence of this. So let's just quickly look at it. So I X Y, this is H of X minus. So this is not H of X minus H of Y given X. This is H of X minus H of X given Y. Right? So this is the correct formula for the mutual information. Now this is concave in PX. In PX. But at the outset it is not clear whether this is a convex or a concave function in PX, right? Because it depends on PX given Y.
Okay.
Right? So it's not, you can't directly conclude just because H of X is concave, you can't directly conclude that the mutual information is a concave function of Px, because you don't know what the second term will look like.
Sir, I had one more query regarding exam.
Yes.
Sir, I have an intensive exam at 7 p.m. Today. I will try to submit it by midnight, but if I can't, can you allow me for some more time?
No, that is hard. So how much more time? How long is your exam?
Yeah, I don't know it yet.
Okay, when was this exam announced?
Yesterday evening around 7 p.m.
Okay, so that's going to be hard because I need some coordination. So send me the details of this particular exam and then I'll see.
Okay, I will email you.
Sure.
So can you explain the concept of stationary erotic process? Like, will it be applicable here? Because in one of the lectures you mentioned that.
Sure. So that's something that we might see a little bit in source coding. So let's go back to this particular thing, right? So let's recall what is a stationary process or a stationary sequence is one where, so you have a sequence x1 through xn. It is stationary is if, of course, all the marginals are the same. Let me write it here. X1 through xn is stationary if whatever. So certainly the marginals are all the same, and you take any subset of random variables and you take a shift of the indices, then the PMF again remains the same. But let's just look at this particular property of stationary sequences. If I want to compress this particular sequence, then the expected length, the minimum expected length, is h of x1 through xn. Okay, and therefore the optimum rate would be equal to the limit as n tends to infinity, h of x1 through xn divided by n. We've only seen IID sequences so far, but as I mentioned, the results that hold true for general for IID sequences, that is, say, the rate of the optimal rate of compression, also carries forward for stationary and ergodic processes. And the reason why that is true is because, in general, for an arbitrary sequence of random variables, this limit may or may not exist, right? If I take an arbitrary sequence of random variables, then this limit may or may not exist. On the other hand, if xn is stationary and ergodic, then this quantity always exists, right? For any stationary and ergodic process or a stationary and ergodic sequence, this quantity always exists, and it's called the entropy rate of the sequence. So we know what the optimal rate of compression is, the asymptotic optimal rate of compression is for any stationary and ergodic process. But if it is not stationary and ergodic, then we cannot conclude what the optimal rate of compression is. The source coding theorem holds only for, at least it generally holds only for stationary and ergodic sources.
Okay, sir. All right. Thank you.
So it's just a generalization. So that is why there's a lot of recent work. I mean, so the problem of compression of stationary and ergodic sources is generally solved, more or less. So if you take any standard text compressors today, these will perform very well and attain the optimal rates for large stationary and ergodic sources. But on the other hand, like there are a lot of problems. For example, compression of genomic sequences or compression of various time series data and so on, where the corresponding sources are not stationary, they're not ergodic. There's a lot of long range dependence, and the dependence can be very weird. So if you try to use a generic compressor like zip or RAR or something like that, it's going to perform very badly. And in fact, designing compressors for non-stationary sequences, that is still fairly open. Any other questions?
Also, regarding the quiz too, like, is there a possibility that people who missed, they can retake it?
I'm sorry, I can't hear.
Oh, sorry. Can you hear me, sir?
Yes.
So regarding the quiz too, as I mentioned in my last class, I kind of missed it, unfortunately.
Sure, I'll make an announcement regarding a makeup quiz.
Okay. So, okay, sir. Wait for it. Thank you.
Okay, so if there are no further questions or comments, then we'll end this class. See you all.